Hello all. So today we will talk about problem 8.8, and this is called RLC circuit via vectors, where we represent certain quantities. We represent the voltage with vectors, which is really interesting. So let's first try part A. Part A is trying to let us verify this formula here. What is this formula exactly? Well, it is Kirchhoff's voltage law. And this law says that when we loop through a circuit, the potential difference is always zero. So the voltage source here provide an EMF, and as we go through individual components, when the current goes through each individual component of the circuit, the cause voltage drops. And then when they all add up, when they all add up, we get zero. And so this is where that formula came from. And now it's telling us to try to verify that it is equivalent to this form. And so let's try to do that. This is, for part A, it is just a plug and chug kind of question, since we are already given I of t, which is I0 times cosine omega t plus phi. So let's try to find the first term first. So L di dt. So it'll be L times d dti. And so it'll be L. Let's try to differentiate this. I0, since it's just a constant. And then what's the derivative of cosine? It should be negative sign. So let's put a negative sign here, and then we have sine. And don't forget the chain rule here. So omega t plus phi becomes omega, and so we have omega here, and then omega t plus phi equals to L di dt. Now it is still a bit different from this form, which has cosine in it. So let's try to convert this to cosine. How can we do that? Well, let's try to cover some knowledge about the sine and cosine conversion. So, of course, I can do this by just telling you the formula for sine a plus b and cosine a plus b, like this formula. But I think it will be easier and easier to understand if I present this in a graphical way. So just keep in mind that this is one of the methods that we can use to find the conversion between sine and cosine. But right now, I would like to just focus on graphically what's happening here. So let's say we pick a value here. Let's say we pick a value here. What does that value correspond to? Well, on the cosine curve, it corresponds to this value. And what's their difference? Is pi over 2, difference here. And so then we see that sine x, or why don't we call this point theta? So this point right here is theta. Then can we agree that sine theta equals to cosine theta minus pi over 2? And so this is the conversion we can do. So let's try to write that. And L di dt equals to negative L, or let's try to write it in the form the question writes it. So negative omega L I0 times cosine. So this is basically the theta. So it'll be omega t plus phi minus pi over 2. It is still a bit different because we have a negative sign here, but on here it is plus. So let's try to make this formula in a negative form. So since we have a negative sign here, what does negative sine theta equal to? Let's try to see. So let's take this theta point again. So this point has value 1. So let's try to find a point on the cosine curve that has value negative 1. And what point is that? It is the point when it is equal to pi. And again, they lag by pi over 2. But this time, cosine leads sine. And so sine theta, negative sine theta, equals to cosine theta plus pi over 2. And so this way, we can just write it as L di dt equals to omega L I0 times cosine omega t plus phi plus pi over 2. And so just to make this clear, this part equals to this negative sign with this sine part. And that is the conversion between sine and cosine. And it is very useful. And so that is the first term. It matches what the question provides. And so next, let's try to find the next term, Ri. So this term. This is really straightforward since we already have I. So just to refresh, I of t, the question gave us I0 cosine omega t plus phi. And so Ri is just R I0 cosine omega t plus phi, which again matches the second part of this question, the second part of this formula. And for the third part, we have Q over C. What do we know about Q? Q, as we know it, it represents charge. Its unit is coulombs. And so it is the integral of the current with respect to time. Why? Because current just measures how much charge flows through every second. And if we take the integral of that, we measure how much charge flows through I every t time. And so that equals to Q. And let's try to do that. So we have from 0 to t, I0 cosine omega t plus phi dt. And again, we can bring I0 to the front because it is a constant. And then for this cosine omega t plus phi term, we differentiate this and we bring it to the front, so it'll be 1 over omega. And then what's the integral of cosine? It is just sine t. And so this becomes sine omega t plus phi. And then we have a constant of integration, which we can set as 0. Why? Well, because we know that from the question, at time equals to 0, the capacitor doesn't have any charge. And so Q should be 0, at 0. And what we also know is that this charge in the capacitor oscillates around the 0 point. So it doesn't really matter this constant of integration. And so then we know Q over C equals to I0 over omega C sine omega t plus phi, which again, not surprisingly, matches the formula here. And then let's just try to do the sine and cosine conversion here again. So previously we said sine theta equals to cosine theta minus pi over 2. And so theta is omega t plus phi, so it's just I0 over omega c cosine omega t plus phi minus pi over 2. And so now let's assemble our equation. So we have omega L I0 cosine omega t plus phi plus pi over 2 plus R I0 cosine omega t plus phi plus I0 over omega c cosine omega t plus phi minus pi over 2, and they all should equal to theta naught cosine omega t. And so that matches our formula here. So just to double check, first term, it matches. Second term, it matches. And the third term, it matches. And so that is our answer to part A. Now that we've done part A, let's work on part B. So part B is asking us to graph these voltages as vectors on the complex plane and see the quadrilateral it forms and use that to verify the formula again. And so how can we do that? Well, first, let's remember that sine and cosine, they're all sinusoidal. And what does that mean? Well, it means they oscillate. And so it's very hard to analyze their behavior sometimes. And so it would be really nice if we can represent them as just vectors. And then we can do sum, we can do subtraction, which is much, much easier than just using sinusoidal graphs. So how can we do that? Well, there's this Magnetism formula called Euler's formula. It is extremely useful here. It basically says that e to the power of I theta equals to cosine theta plus I sine theta. So I represents the imaginary unit. And so this formula is very useful because then we can plot this on a complex plane. So a complex plane has real number, the real part of this number, so as the x-axis, and the imaginary part of this complex number as the y-axis. And so as you can see here, we have a very clear divide between real and imaginary. And so then we can just say for any vector that its a horizontal projection onto this horizontal real axis is just cosine of that theta. And then for y axis, it's just sine theta. And that is how we can turn this into vector, turn these sinusoids into vectors. So as you can see, we can easily write that the real part. So this RE represents real part. The real part of EI theta just equals to cosine theta. And so then, can we agree that this expression, this cosine omega t plus phi plus pi over 2, is just the real part of E I omega t plus phi plus pi over 2? And so then we can graph this vector. And with the same method, we can graph all three. And then afterwards, we'll see what kind of quadrilateral it forms. And this will also be graphed onto the complex plane. So let's try to write out all formulas in this form first. So R I0, or I'm gonna just omit these terms for now. We'll add them on later. But right now they don't really matter. So let's just do this term first here. So cosine omega t plus phi, it's quite straightforward. It's just RE, and then the real part of the E I times omega t plus phi. And then let's look at this term. Again, it's just cosine omega t plus phi minus pi over 2 equals to the real part of E I omega t plus phi minus pi over 2. And then for this, epsilon naught, epsilon 0, cosine omega t is just the real part of E I omega t. And so how is that useful? How can that help us? Let's try to graph it now. So let me draw the complex plane first. So here we have the real part. We have the imaginary part as the y-axis. And just keep in mind what these numbers are. So if we just only focus on this exponential, let's ignore the real part. This number is complex. So what does complex mean? Complex means it's a plus bi. It has an imaginary part and it has a real part. And the real part is the one we care. But let's not forget this part too, because we're graphing them on the complex plane. And by writing this in the real part of some complex number, that's the only way we can draw these sinusoids into vectors. And so let's try to do that. Well, can we just first assume, let's just say omega t equals to 0 at this point for now, because it doesn't really matter what omega t is. We can always shift. I'll explain a bit more later, but let's first look at what epsilon would look like. So it would be E I times 0. And so it is just E to the power of I times 0 is just E to the power of 0, which is 1. And so let's just draw here. But keep in mind the magnitude is not 1. So, sorry, I made a mistake here. It should be just cosine omega t equals to the real part of E I omega t. And then if we couple that with omega 0 cosine omega t is just the omega 0 times the real part of E I omega t. And as we said before, let's assume omega t to be 0. And so this is just epsilon 0. And so this vector has magnitude epsilon 0. And now let's consider the next vector. Let's look at this vector here. So for this one, its coefficient is I0 over omega c. So we have I0 over omega c cosine omega t plus phi minus pi over 2. And so it is I0 over omega c times e to the power of, or the real part of e times I omega t plus phi minus pi over 2. And remember we said omega t to be 0. And so it is I0 over omega c times the real part of e I phi minus pi over 2. And for now we need to define some sort of phi. So why don't we just define phi can be literally any angle. Let's just say that phi is just this angle here. And then minus pi over 2, that means we're rotating it clockwise. So remember, anti-clockwise is positive as of convention. And so minus pi over 2 means rotating this by pi over 2 clockwise. And so what would that look like? So if we draw that, it will look like this. And then its magnitude, again, is just I0 over omega c. And so let me just draw that. We'll have I0 over omega c. And here it's a right angle. And now let's look at our next term. And so for the next term, we have cosine omega t plus phi, which is the real part of e I times omega t plus phi. And it corresponds to this term here. Its coefficient is Ri0. And so let's try to do that. So Ri0 cosine omega t plus phi is just Ri0 times the real part of e times I omega t plus phi. And then we said that omega t is 0 here, and so e I phi, and its magnitude is r times I0. So just write along this line here. And just to draw it, we have r I0 here. And the angle is just phi. And now let's do the next one, the last one. For the last one, we have cosine omega t plus phi plus pi over 2. And it corresponds to coefficient omega 0, omega L I0. And so omega L I0 cosine omega t plus phi plus pi over 2 is just omega L I0 times the real part of the exponential e to the power of I omega t plus phi plus pi over 2. And again, omega t is 0 here, so it's just omega L times I0, the real part of e I phi plus pi over 2. And now it is plus. So what does plus mean? Plus means rotating clockwise, anti-clockwise. And so then we just need to rotate this purple vector here by 90 degrees, and that's the angle we want. So let's try to draw it. And remember that the magnitude here is omega L I0. So let's just try it like that. And then that is 90 degrees, and its magnitude is omega L I0. And so just to make this a bit more clear, let me just explain once more how this works. So we said, take this vector for example. It is omega L I0 times e to the power of I omega t plus phi plus pi over 2. And now if we just look at this y-axis, the height of this vector, it is just the imaginary part of this expression, and that is the height. And what about the real part? The real part of this expression is just the horizontal length. And the horizontal length is the quantity that we care about. But then we need to write both so that we can graph this sinusoidal function as vectors on the complex plane. So the question is asking us if the sum of this vector, and that vector gives us this vector. So how can we do that? Now let's try to represent that sort of visually. So how can we arrange these 4 vectors so that they end up in a setup that's very clear to see that their sum yields, these 3 vector sums yields epsilon 0. So what if we move this Ri0 to here? So just let me switch the color. What if we switch this to be Ri0, and then we'll have omega L I0 here. And so first I want to just say that hand drawing is very inaccurate, so it might seem off on the screen, but actually when we actually get the real data, and we draw these vectors according to these data, like the magnitude, we draw them according to the actual magnitude, we will get a quadrilateral that is like this. But right now, since I'm just hand drawing it is very difficult to draw them very, very realistically. And so, but the big point, the main idea here is that they form some sort of quadrilateral here. And keep in mind that this whole shape, they rotate at speed omega. Remember that omega t term? So as t increases, this whole setup sort of rotates around this plane. And so they rotate at angular speed omega. But the point is, this shape doesn't change. Every single vector, these four vectors, they all together, they rotate at angular speed omega. And so this relationship of these three vectors sum giving out epsilon 0 is always true no matter what. And so this is our answer to part B, our visual representation. And if you're still feeling a bit uneasy about how I said like my handwriting isn't accurate, we will verify it algebraically in the next part, in part C, where we actually manipulate quantities using some geometrical properties, and then finally checking against a correct formula that we derived using just sinusoidal functions. And so by just checking the results, I think you'll be more convinced that this visual representation is correct. So now let's move on to part C. For part C, it is asking us to use our quadrilateral to determine the amplitude of I0 and the phase phi of the current, and check that they agree with the values in equations 8.38 and equations 8.39. And so these two equations, 8.3 and 8.39, are all from the book. And just since there's a bit of a lack of context, I just want to say that these two formulas, like the 8.3 and 8.39 formulas, they are all derived using actual sinusoidal functions, so using sine and cosine, and then using them trig identities like cosine A plus cosine B and sine A plus sine B. And so we are sure that equations 8.38 and 8.39 are always correct. So let me just write it down here. What are 8.38 and 8.39? Well, 8.38 says that I of t equals to epsilon 0 over square root r squared plus omega L minus 1 over omega C squared times cosine omega t plus phi. And then tangent phi equals to 1 over r omega c minus omega L over r. And so these two things, they are for RLC circuits. That means you have a voltage source, you have a resistor, you have an inductor, and you have a capacitor connected in series in a circuit. And so for any circuit that looks like this, that has an AC voltage source, the formulas are always this. And so now let's check this geometrically and see what we get. So let me just redraw the quadrilateral here in a better way. So we had this. And we said this is Ri0 pointing upwards. This is omega Li0. This is epsilon 0. And this is I0 omega C. And so just to mention something else, like they connect head to tail. And so that's how the sum of vectors work. So when we plus all three vectors, we're connecting them head to tail, which as you can see, we come back from here to here to here, we come back to epsilon 0. And so that geometrically. But what about algebra? So we're thinking maybe let's try to use Pythagorean theorem since we have a right triangle here. And we know that this side, the side length, is I0 over omega C minus omega L I0. And we know that this is Ri0. And so what can we do? Well, we need an angle somewhere, and how can we do that? Well, look here, we have a phi here, and then we have a vector, and this is 90 degrees. So doesn't that mean that this angle is just 90 minus phi? And so now we know this is 90 minus phi, and obviously this just becomes phi. Because the interior angle sum of a triangle is always 180 degrees. Okay, so now we have all the things that we need to use Pythagorean theorem and use some trig. So let's first try Pythagorean to get an expression for this first. So first I would like to get a common factor out. So we have I0 over 1 omega C minus omega L. and that is this length of the right triangle. And so now we have epsilon 0 squared equals to I0 squared 1 over omega c minus omega L squared plus R squared I0 squared. And epsilon 0 just equals to I0 square root R squared plus 1 over omega c minus omega L squared. And then now if we rearrange this a bit, we get I0 equals to epsilon 0 over square root R squared plus 1 over omega c minus omega L squared. So this formula that we got agrees with this expression. Since remember that I0, it doesn't really represent the current at time 0, it just represents the maximum amplitude of current. And so obviously the max value cosine can obtain is just 1. And so the I of t, the maximum I of t, matches our expression here. And just keep in mind that always a minus b squared always equal to b minus a squared. Since b minus a and a minus b only differs by a sign, a negative sign, but square sort of just remove that negative sign and makes everything positive. And so we can alternatively write this as epsilon 0 over r squared plus omega L minus 1 over omega c squared, which agrees with the first formula. And now for next formula, we have tangent phi. Tangent phi, we said this is phi, so it is I0 1 over omega c minus omega L over r I0. And so we have 1 over omega, let's write it in the formulas form. So 1 over r omega c minus omega L over r, which again obviously matches with the second formula. And so that is our answer to part C, and it sort of just verifies that our geometric representation is correct, and it provides a very new and very simple way of visualizing and calculating and manipulating these sinusoidal functions. Otherwise, we would have just used sine a plus b formulas and like cosine a plus b formulas, which is fine, but they're very complicated and they're long and hard and boring to do. So this question is very interesting. It gives us a new perspective. Thank you for watching.